I did my PhD in the Julia programming language, and lately I wanted to learn more about C++. And so what I decided to do is trying to re-implement what I did for the third paper of my PhD called Supervised Large Neighborhood Search for MIPS. So in this paper, we study how we can use supervised learning in LNS to accelerate MIP solving. So I worked on this project called solver-cpp, where I implement LNS, I experiment with Gurobi, and then I run a bunch of experiments to be able to demonstrate the ability of LNS to accelerate MIP solving for MIPLIB instances. There's a few dependencies and set up installations in the README if you are interested in reproducing. All the code is open source. So you can see here on there's a live app where you can have access to all the information that's connected to the database and all the results. So the first thing that we need to do is select the binary variables or the instances with binary variables. So we check if the number of binary variables is not null, and then after filtering instances for which we cannot find any solution or that we've solved to optimality using Gurobi after 10 seconds, we do some filtering from 227 to about 60 instances. So we filter based on the MIP gap, which allows us to assess the difficulty. So we set to selected 61 instances, and then we run our experiments on them. To assess performance, we use the primal gap, which is the gap relative to the best known solution for a given instance. We compare our baseline warm start with LNS. So we call it warm start because all we're doing is taking the best solution that we found using Gurobi only, and then we pass that to the solver. We compare this to LNS, where we randomly select a subset of variables given a fixing ratio. And so all jobs here have a time limit of about 10 seconds, and we run them with 3 different seeds. You can see here we have 3 times more results for these runs because we have 3 seeds. So in this table, we have the summary of the primal gap, the group name, so the LNS with different fixing ratios versus warm start, number of wins, the average primal gap, standard deviation, and different quantiles or percentiles. Notice that LNS with the fixing ratio of 5% has the most number of wins, the smallest primal gap, the smallest standard deviation, but it doesn't have the smallest median. So also has the smallest 75th percentile. The main takeaways here I'm going to summarize. So first is that a smaller fixing ratio is better here, mostly because we're working with small instances. If we had very large instances, then a larger fixing ratio could be beneficial. Also notice that we have 2 orders of magnitude between the primal gap, or the average value, and the median. That is probably because we have some points where the primal gap is very, very large, and that skews the average. So if your goal is to have the best performance in the majority of problems, and you can tolerate an occasional poor result, warm start looks good. It's more often the winner on a typical instance. So because of the median being the smallest. So if your instances is somewhat small or average, then it's probably better to use a warm start. But if the instances is harder, then LNS with the appropriate fixing ratio can bring down significantly your average primal gap. So this is what we're saying at the end. So if your goal is to have the most reliable performance, right, because we have the most number of wins, it's a good source. It might not always win on easy instances because we are modifying the original instance. But it's more stable and avoids extreme performance degradations that hurt warm start's average. In the end, if you're interested in looking more into the details, here I'm querying all the tables in the SQLite database for your curiosity, and you can also run an SQL query if you want to. Once again, everything is available at solver-cpp.fly.dev. Thank you for watching. Bye-bye.